Blackbody radiation occurs when an object absorbs all incoming electromagnetic waves and re-emits them as thermal radiation. Classical physics attempted to explain this phenomenon using electromagnetic theory. According to classical physics, the energy density of radiation inside a cavity should follow the Rayleigh-Jeans law, proportional to frequency squared divided by temperature. This graph shows the classical prediction in orange, which increases without bound at high frequencies. The experimental data in teal shows a peak followed by a decline. The ultraviolet catastrophe demonstrates that classical physics could not accurately describe blackbody radiation, setting the stage for quantum mechanics. Max Planck proposed that energy is quantized, existing only in discrete amounts rather than continuously. This revolutionary idea solved the ultraviolet catastrophe by limiting high-frequency energy modes. The ultraviolet catastrophe occurred because classical physics allowed oscillators to have any amount of energy, leading to infinite energy at high frequencies. Max Planck hypothesized that energy is quantized, meaning it comes in discrete packets rather than any amount. The energy E of each packet equals Planck's constant h multiplied by the frequency f. Planck's constant h is a fundamental constant of quantum mechanics with the value 6.626 times 10 to the power of negative 34 joule-seconds. It determines the scale of quantum effects. Energy levels are now discrete. E equals 1hf, 2hf, 3f, and so on. Oscillators can only occupy these specific energy states. Transitions between energy levels involve absorbing or emitting energy packets of hf. By quantizing energy, Planck limited the number of high-frequency modes that could be excited, resolving the ultraviolet catastrophe. Wave-particle duality is a fundamental concept in quantum physics, stating that both light and matter exhibit both wave-like and particle-like properties depending on the experimental setup. Historically, light was thought to be purely a wave, while matter was considered purely particles. Quantum mechanics revealed this duality through experiments. The photoelectric effect provides evidence for light's particle nature. When photons strike a metal surface, they can eject electrons if the photon energy exceeds the metal's binding energy. Each photon transfers its energy to an electron. The electron gains enough kinetic energy to escape the metal surface. The photon energy is given by E equals h nu, where h is Planck's constant and nu is the frequency. This explains why there's a threshold frequency for the effect. Compton scattering further demonstrates light's particle nature. When a photon collides with an electron, both behave like particles in a collision. The photon transfers momentum and energy to the electron. The scattered photon has a longer wavelength, confirming particle-like momentum conservation. Louis de Broglie proposed that matter particles, like electrons, exhibit wave-like properties in addition to their particle nature. This relationship is expressed as the de Broglie wavelength, where lambda represents the wavelength, h is Planck's constant, and p is the particle's momentum. The wavelength lambda is the distance between consecutive crests of the matter wave. Momentum p is the product of the particle's mass and its velocity. It determines the wavelength of the associated matter wave. An example of matter waves is electron diffraction. When electrons pass through a crystal lattice, they create diffraction patterns similar to light waves passing through slits. The double slit experiment demonstrates this most clearly. When electrons pass through two slits, they produce interference patterns on a screen, just like waves would, confirming their wave-particle duality. Heisenberg's uncertainty principle reveals a fundamental limitation in our ability to know the quantum world. It states that we cannot simultaneously measure both the position and momentum of a particle with perfect precision. This principle arises because measuring one property inevitably disturbs the other. The more precisely we know a particle's position, the less certain we are about its momentum, and vice versa. Mathematically, this is expressed as delta x times delta p is greater than or equal to h bar over 2, where delta x represents the uncertainty in position and delta p the uncertainty in momentum. To illustrate this trade-off, consider a particle. If we measure its position very precisely, it appears as a sharp point, but this means its momentum becomes highly uncertain, represented by arrows in many directions. Conversely, if we measure momentum precisely, shown as a single arrow, the position becomes spread out like a wave, increasing its uncertainty. Heisenberg's principle shows that quantum mechanics is fundamentally probabilistic. Particles don't have definite positions and momenta simultaneously, but rather probability distributions. The uncertainty principle sets the minimum spread of these distributions. In quantum mechanics, the wave function, denoted by psi, completely describes the quantum state of a particle. The square of the wave function, psi squared, gives the probability density of finding the particle at a specific location in space. Hermitian operators represent measurable physical quantities called observables. These include energy, momentum, and position. The Schrödinger equation describes how the wave function evolves over time. It relates the rate of change of psi to the Hamiltonian operator, which contains the energy information. Quantum technologies represent the cutting edge of modern computing and information processing. At their heart are qubits, the fundamental units of quantum computers. Unlike classical bits that can only be in one state at a time, either 0 or 1, qubits leverage superposition to exist in multiple states simultaneously. This quantum property allows quantum computers to process vast amounts of information in parallel. Several hardware platforms are being developed to implement qubits. Superconducting circuits use electrical circuits cooled to near absolute zero. Trapped ions involve individual atoms held by electromagnetic fields. Topological qubits rely on exotic particles and special materials that are inherently stable. Quantum computing holds tremendous potential across many fields. In drug discovery, quantum computers can simulate molecular interactions with unprecedented precision. Materials science benefits from the ability to design new materials with specific properties. Cryptography applications include both breaking current encryption methods and developing quantum-resistant security protocols.